Alright, so I'm just gonna do a quick recap of the Laplacian of Gaussian filter. Not sure how it's pronounced, to be honest. Yeah, Slay is on this document right now. Okay, so it's pretty simple. This is gonna be a quick review. So the way it works is you have an image, right? And you have pixels. So basically, you're going to have a 3 by 3 filter, which is what I have here, and that filter is going to be applied to every single pixel. I don't know how it's going to work on the edges. Yeah, I don't. Um, but for the ones like similar to shown here, where all members are within the grid, what you have is actually, let me start from the top. So the Gaussian function, it assigns each pixel a brightness based on that pixel's neighborhood, uh, that pixel's neighborhoods, no, that pixel's neighbor's brightness. Yeah. Um, yeah. So we have a formula. This is the formula here, and yeah, this is the formula there. And basically, you're gonna put in the coordinates from what the fuck am I saying? Okay, I guess this will be run one. So this is your formula here. So it calculates each member's weight of the community. Each member in the communities, each calculates the weight of each member in the community. Okay, so you input the codes for the members, and the codes are all referenced to the center pixel. So yeah, whenever you slide the filter, all the respective positions are gonna have the same weight. Yeah, you're gonna have the same coordinates actually, and because they have the same coordinates, they're gonna have the same weight. So yeah, after you get the weight, for example, here, this guy here, top right, it's the same for all actually. When you get the position's weight, you multiply the weight by the brightness of that pixel, and you do it for all positions. I'm not sure if you do it for the center actually. I'm not sure if you do it for the center, but for sure you do it for the neighbors, and then you sum up all the brightnesses, and then this is what you use for your brightness in the middle. So that's that. Yes, that's what I mean by multiply by original brightness, multiply the weights by it, and that's it. Use it for your new pixel value in the center. Right? Great. So to break down your formula here, our formula here, the way it works is, so this minus sign is what causes decay. If it was positive, then it would grow. It would cause growth, but that causes it to decay. Okay, so actually, let's start from let's reverse engineer it. So this formula gives you the weight of your neighboring pixels, right? You're in the center, and then you have neighbors. It's supposed to be like a square. You have neighbors, right? In the center, you have the strongest weight. As you leave outward, your weight decreases. That function tells you how much the weight decreases by. So you put in the coordinates of this point, and it tells you the weight of this point based on this reference point. That's what the function does. So now that you know what the function does, yeah, this minus sign causes decay. What else? This fact that we're using e here, the e function, causes our decay to be natural. Like it decays naturally. If we used, because E I think is maybe 2 or 1.7 or some constant, right? But if we just use like a 2 or 10, some normal integer, then the decay would be like not so natural. It would be kind of harsh, or kind of not natural. I want to say spiky, but not as natural or smooth. So that's what the E does. The 2 pi just splits the weight into 2 pi pieces. So it's one whole, but divided by 2 pi pieces. When you sum up everything, it's gonna add up to 1. Yeah, this standard deviation squared, it determines how much it determines the decay amount. So it determines by how much your weight varies with distance. That's what this does. This is the same thing in the denominator position, so it actually does the same thing. This 2 next to it, this guy over here, it actually slows decay. So your decay looks like this. This is called a Gaussian bell, which is why this is under the Gaussian filter. So without the 2, it would look more narrow. With the 2, it looks more wide. So the 2 basically slows the decay. Yeah, around the center pixel. And the x plus y, I don't have it marked, but it's just for positional variation. And actually they're squared because they're squared so that I think the distance in any direction is positive or something like that. I don't exactly remember. Last chat, it said something about the distance. So I guess it's like even if you're going to the left or right, whether you're going to the left or right, it's gonna calculate just distance, not direction. So that's it for this guy. And the process which we have up here really just seems to be you take the G formula, differentiate it with respect to x, you're gonna get this. Alright, boom boom boom, that's that. Then you differentiate it again. So you take its second derivative. Alright, differentiate it again. You get this guy, or this guy, same thing really. Boom boom. And yeah, with your second derivative, you just pretend a y was there. Apparently it's gonna come to the same thing, which is this over here. And then to actually get the Laplacian of Gaussian formula, you just add the second derivative with respect to x and y together. So this is it here, x and y. Sum it up, and yeah, you just simplify. You have this, you simplify it, and then eventually you factor it, and then it ends up looking like this, and that's your answer. So not too crazy. Not too crazy. Yeah.